You're on the air. Yes.
Right, but I'm lazy, so when I write on the board. Okay, so I'd like to thank very much the program organizers for having given me the opportunity to come back for a second visit to this workshop. I regret not being on sabbatical this semester, so I can't stay for more than a couple of weeks here and there, but it's been great. And also for having said, you do want to give a seminar talk, don't you? So, oh, well, I suppose. So it's going to give me a chance to talk about a long-term ongoing project with Brooke, which this program has actually, I think, given us the opportunity to complete, or at least the first paper in the series. I'm going to talk about work that should have preceded, should have appeared before an article that has already appeared, but that's life when you have two co-authors who are both very busy. So anyway, I'm going to talk to you about what topological coHochschild homology is, and why we care about it, and what its properties are, and things like that. So first I'm going to start with a little introduction. This is for some motivation, why you should even care about this. So motivation, I'm going to talk about free loop spaces. And Hochschild homology. So free loop spaces were my first topological love before I fell in love with configuration spaces. And well, I'm still somewhat faithful to free loop spaces. I think they're wonderful. And so let me remind you of what free loop spaces are. So we take a topological space X, then we're looking at the space of all continuous match from the circle into the space X, equipped with compact open topology usually. And one nice thing about this is that it fits into a fiber sequence that looks like this. Base loops, okay, let's fix a base point in X. Then we can include that into the free loop space, and then you have an evaluation map on X. Very nice vibration. And it gives us a vision of this free loop space as sort of built from twisting together the space X with its base loop space. And if X is actually harkening back to the previous talk, BG, so the classifying space of some topological group, then we can actually think of this sequence as looking more like this. So G itself going into the free loop space, and then down to BG. So, or you could think of something more general than just a topological group. So my original goal, many years ago when I first started thinking about free loop spaces, was to build some kind of an algebraic model for the free loop space, because I was interested in free loop spaces and their relationship to, for example, topological cyclic homology, or because of their role in the accounting geodesics on manifolds and things like that. So the original goal was to get some sort of algebraic model for the free loop space in terms of some sort of algebraic model, some sort of chain complex type models for the space X and for the base loop space. In terms of models for X and the base loop space, or if you're thinking about the free loop space on BG in terms of some sort of model for BG and some sort of model for the group G itself. So the first step towards these goals is to figure out what I'm going to mean by algebraic models of the base loop space or the classifying space of a group. So first step is to think about some sort of BG analogs of the base loop space and the classifying space. So these are well known to all of us. We have, on the one hand, functor, which I also call omega, which is the cobar construction, going from a category. I'm just going to write co-alt k. So throughout this talk, I'm going to work over a field. A lot of what I'm saying could actually be done over an arbitrary commutative ring, but let's keep things very simple and work over a field. So here I'm thinking about differential graded co-associative coalgebras, which I'm thinking of as connected. So these are connected, co-augmented, so they don't just have a co-unit, they also have something that looks more like a unit mapping K into the coalgebra, e.g. coalgebras over K. And on the other hand, we have a right adjoint from the category of algebras, bar construction, reduced bar construction. So here it's just augmented e.g. algebras, non-negatively graded. So everything I'm thinking about quadrats and algebras, I'm thinking about things that are non-negatively graded. More generally, when I talk about chain complexes, they may be unbounded. So this is our bar construction. And the co-bar construction. And we can build these things. Everybody, I imagine, knows how these things are constructed. This is some sort of free tensor algebra on a desuspension of the co-augmentation co-ideal. This is a co-free tensor co-algebra on the augmentation ideal, with a differential in each case that's built from the differential of the underlying object, together with, in the case of the co-bar construction, it's co-multiplication. In the case of the bar construction, the multiplication goes into building the differential of the bar construction. So what's important about this, the topological relevance, is as follows. It's that if X is, say, in a simply connected space, and I take the co-bar construction on the chains on X, and I'm being a little bit, I'm actually thinking about simplicial sets, and I'm taking normalized code chains, but let's just be a little bit loose about exactly what I mean. So the co-bar construction on the chains on X, which is itself a DG coalgebra, is equivalent to the chains on loops X. This is Adams' result. And then we also know that for any X, if we take the bar construction, on the chains on G, which is a DG algebra, then we get something which is equivalent to the chains on BG.
Wait a minute, what do you mean for G?
Sorry, G. G became X. So in this case, why do I care about doing something like this? Well, if I think about what I have on this side, it's a DG algebra because the base loop space, I think about the more loops, for example, so I actually have a strictly associative product, or I'm thinking about the con loop group construction on something simplicial. So I really have an honest associative DG algebra on this side. Yes, it's a DG algebra, but its multiplicative structure is very complex. The advantage to this model here is that this is a free tensor algebra. The multiplicative structure here is much more simple. So this is a lot easier to understand and to work with than what you have on this side if you're trying to do actual computations. And similarly on this side, here the coalgebra structure is complex. So on this side, well, it's somewhat complex, and on this side you have this co-free factor. So that's one reason why one might care about these kind of models. So the idea now, notice that it's not visible when you write it. So the idea here is to now build a model for the chains on the free loop space from this co-bar construction and chains on X. And just sort of twist them together in some way, just as the free loop space itself is sort of twisted together from the base loops and the space X. And for the chains on the free loops on VG, from something like chains on G and the bar construction. Something you can hope to be able to compute with. So let me talk about what works in the case of BG. So the tool in the case of BG is Hochschild homology. So the thing about the Hochschild complex functor. So it's some functor from, I'll write H like this, from my category of augmented algebras to chain complexes, which is built really by twisting together an algebra and its bar construction. Let's see. Don't want to write it out explicitly, so which fits into a sequence that looks like this. So if I have a BG algebra A, then it includes into its Hochschild complex, and the Hochschild complex then projects off onto the bar construction. This thing looks like some sort of twisted tensor product of these two constructions. So it's the underlying chain complex, sorry, the underlying graded vector space is the actual tensor product, and the differential sort of twists the things together. I'm not going to describe it explicitly, except that I will say in a moment something about how we can build it as some kind of geometric realization. Okay, so why is this something that we care about? Let's think about its topological relevance. So, let me just say one more thing. So, then the Hochschild homology of A, which will look like this, is just the homology of this complex. All right, so why should we care about this? As topologists, so the topological relevance of this construction is a theorem that is due to a number of people. So there's a theorem proved back, I think, mostly in the 80s. There's part of it that's due to Goodwillie, part of it that's due to Borgheri and Fedorovitz. Part of it is due to Jones. So those are for the work that was done in the 1980s, getting isomorphisms of graded vector spaces, and then when you want to get some multiplicative structure as well, there was work by Minicki, and then there was work by Ndomboz. And so lots of names to put on this, but what we know is that if X is a pointed connected space, then if we calculate the Hochschild homology of the chains on loops X, what we get is the homology of loops X. So the original isomorphisms were given linearly, and then Minicki, I think Minicki did that one.
Too many omegas.
Too many omegas, yes, right, so that's an L. Thank you. Ndomboz and Thomas proved that it was actually, you could actually get an isomorphism of algebras. And then, if X is one connected, then the Hochschild homology of the BG algebra, which is the cochains on X, is actually isomorphic as an algebra when you give the right kind of structure to the cohomology. So that this gives us, this algebraic construction is perfectly topologically relevant for us. But I'd like to say a few more things about Hochschild homology besides its connection to free loop spaces, because when I talk about coHochschild homology, I want to sort of dualize the properties, then I'll be mentioning that. So, I suppose that what I'm writing now can be interpreted two ways, that there's more interesting properties or more interesting properties. You can choose. So the first one is that one way to understand where this Hochschild complex functor is coming from is that the Hochschild complex of A can actually be gotten by taking the cyclic bar construction of A, if you know what that is, and taking its geometric realization. Writing it this way enables one might be able to generalize this beyond the DG world to other monodal categories of interest, such as spectra. So possibility or generalization other monoidal categories. Okay, and we will do exactly that. So, for example, we can generalize it to the category of DG categories, where you look at the DG category as an algebra, DG algebra with many objects, or to whatever your favorite monoidal category of spectra is, or why not to the category of categories, small categories enriched in spectra. So you can think of that as another context in which you can work. Okay, so once we do that, another important property is what's known in some circles as agreement. So there's a work by Randy McCarthy, and then in a more general context by Bernard Keller, who proved the following, that if A is an algebra, then the Hochschild homology of A is actually isomorphic to the Hochschild homology of the DG category of A modules. So we're looking at this as the category of A modules itself as a DG category, so it's a DG algebra with many objects, and so it makes sense to talk about this Hochschild construction, and it turns out that these are actually the same. So I'm just cheating a little. Actually, I shouldn't write mod A, that's not true. It's not all of mod, we don't want that, we want some sort of compact situation. So Bernard Keller called DG free. So these are A modules that are built up in a finite number of stages by free type extensions, quasi-free extensions. So these are essentially finitely generated free A modules. So these are compact objects in this category. And then there's a spectral version of this to Andrew Blomberg and Mike Mandel, who proved the following, that if A is now some sort of algebra in spectra, whatever your favorite category of spectra is, then, let's see, I should just introduce some notation here. When I'm talking about HH in this context, I'll use the standard notation, which is called THH, topological Hochschild homology. When I'm talking about algebras in spectra or spectral categories. So in this case, this shows that THH of A was equivalent to THH of a fixed subcategory of A modules generated by A. So it's the same kind of result if we have an agreement between the Hochschild homology of a ring and the Hochschild homology of some appropriate subcategory of A modules. All right, so that's the kind of result that we would like to want to generalize. Finally, what again in some categories is called Lorentzian variance. So classically, this is the sort of thing that says the Hochschild homology of an algebra is the same as the Hochschild homology of of the algebra of matrices with coefficients in this algebra. But in the DG context, tau n proved the following, that it says that, first of all, it defines what it means by a map between two DG categories, actually the homotopy category of DG categories is what he calls a Merida equivalence. When you look at the induced map between the subcategories of compact, fibrant, cofibrant objects, so you have cofibrant, fibrant objects, here, they're also compact in some appropriate sense, and this is equivalent to the same thing for A prime. We say that if A and A prime are Maurian equivalent, then they're Hochschild homology. And this is some sort of big generalization of the standard Maurian invariance result one knows for Hochschild homology. So that's to remind you of what probably most of you already seen before about Hochschild homology, its relation to two free loop spaces. And now that we've seen these reminders, I can start telling you about coHochschild homology. First in the DG context, as a real warm-up for the spectral context, because that's where life gets difficult, as Brooke has pointed out to me many, many times. And then we'll get to the spectral context at the end. So, let's start by talking about coHochschild homology in the DG world. So, this is where life is relatively easy, where things are relatively straightforward to define. It gets more complicated when you want to do things in spectra. So, what we're going to do is dualize the story that I told for Hochschild homology. So the roots of this are in work of Doi, and there's also an article by Idrisi, where they were talking about doing this sort of thing in a non-differential graded context. And then in work first with Polytechnique and Jonathan Scott, who extended this to the DG world, and then have taken this further with Brooke, and also in work with Alexander. So let's dualize. So the coHochschild complex sponsor, which I'm going to do like this, with a hat on the H now, to go from coalgebras over K into chain complexes. It fits into a sequence that looks like the first sequence that we saw for the free loop space. So we have an inclusion of the cobar construction into this coHochschild thing, and then it projects down onto C. And this one looks something like twisting together the cobar construction on C and C itself. So there's a way of twisting these guys together to get this coHochschild construction. So the definition is strictly dual to that of the Hochschild homology, Hochschild complex. And then the coHochschild homology of C is, well, I write like this, coHH of C is just the homology of this complex. Alright, so why should we care about this? Well, first of all, I'm just going to point out, for those who would like to see the definition, that to compute this thing, we're working in chain complexes and everything is nice, and I have a nice connected coalgebra, then it turns out that this complex I'm defining here is nothing but the totalization, in the usual sense of talking about chain complexes, of a certain co-cyclic cobar construction. So it's co-cyclic cobar, which is some sort of co-simplicity object in chain complexes, with an additional cyclic structure that we're hiding right now. Okay, so this points out that you could generalize this And indeed I will in a little while when I talk about the spectral case. But one thing we could do as a generalization, which I don't think you want to do, because Brooke and I spent some time talking about this and realized that it was rather painful. But you could, if you really wanted to, and a good reason to generalize this to differential graded co-categories. These exist. Bernard Keller has an entire paper about differential graded co-categories. But they are non-intuitive. Shall we put it that way, Brooke? And in the end, we had no good reason to do it, so we didn't. Okay, you really
There are
need.
places where you can decompose a map.
Yeah, you do exactly. You decompose them up into tensor products. Yeah, exactly. I mean, try constructing some examples. It's kind of fun, actually. I mean, if you're glutton for punishment. So what's the topological relevance? Try to stay grounded in topology. So about 10 years ago, maybe a little bit more now, in joint work with Paul-Eugène Baron and Jonathan Scott, we showed that if X is non-connected, then the coHochschild homology of the chains on X is isomorphic to and this is actually, it's not just a result on the level of the homologies, there's actually a map that is a quasi-isomorphism. But at least we see we can compute the homology here. What is the advantage of this? Why should one care about this when one already has the results of Goodwitty and Jones and so on? The advantage is that if I look at this thing, so what I actually have here is a quasi-isomorphism in chain complexes that looks like this. So think about how this one is built. It's some sort of twisting coming from this Hobart construction, which is this relatively nice free tensor algebra with the chains on X. And if you happen to be thinking of X as really a simplicial set, and your changes being normalized chains, and X has only a finite number of non-degenerate simplices, then this guy's actually very small. And this guy isn't very big either. So what you have is actually some sort of model for computing the homology of the free loop space, which might be manageable. Maybe even is manageable with some of the computer technology that we have at hand now. Okay, so that's why one might care about that from a topological point of view. But now let's think about some of these properties analogous to what we saw for Hochschild homology and see what we can say. All right. So first of all, let's consider the relation with Hochschild homology. So you hope that these two had something to do with each other. And indeed, proposition by the same authors says that for every seed, there's a quasi-isomorphism from the coHochschild on C to the Hochschild on omega C. And dually, in algebra, there's a quasi-isomorphism from the coHochschild on bar. So they're nicely linked like this. Now, what is in some sense, in a sense that I'm not going to make very precise, because it's not entirely precise in my head either, I must admit, but it sort of feels the same, and I think we can make this precise. It's sort of a categorification of this. It's a proposition in the paper that Brooke and I hope to submit before I leave, or shortly thereafter, that says the following, that if I have any coalgebra, then there is an enriched, a DG enriched line equivalence between comodules on C and modules on omega C. So the understanding this is a categorification of this is sort of a work in progress, but that really is the feeling that it has. And just wanted to point out that here, so this is it's classical in the sense that it dates back to Schrader and Shipley, that for the model structure. And it's a little, maybe it's newer in any case, that there's a model structure here that's due to Fried, Magda, Emily, Real, and Burke. That's where you can find the sources of these, the model structures, and this turns out to give you a nice differential gradient Coulomb equivalence. Right. That's yeah.
In line 1, the point that why you don't make this the definition of HH hat is because the left-hand side is smaller.
Yes, because this one, if you think about what it looks like this. And bar co-bar is massive. Yes. So this is the left-hand side is a lot smaller. Thanks for asking. Okay, so we have a DG Coulomb equivalence between these two categories. Okay, and in particular, as a corollary of this, we know that if X is simply connected, then there's a Coulomb equivalence this. So why do I need things to be simply connected? Because this is using that I actually have weak equivalence like this. If X is unconnected. And it's just to sort of, again, ground us topologically. Tell us what's going on for topological spaces. So, as long as X is simply connected, we have this relationship between comodules over the chains on X and modules over the chains on X. So this is sort of a sort of thing that doesn't surprise any topologist. Okay, so that's a relation with Hochschild homology. Now let's do some version of agreement. For coHH. So I remind you that agreement is about computing the, well, in the Hochschild homology case, it was about the Hochschild homology of a ring compared to the Hochschild homology of the category of modules over the ring. So in this case, we're going to want to compare the coHochschild homology of a coalgebra and the Hochschild homology of some DG category, because we're not going to associate a co-category, you see, fortunately. And so this is how we go. So we have this category, this DG3 category. DG3 over some A. So we're going to try to do something analogous to DG3, and this is the way we're going to set it up. So
Can I ask a question?
Yeah.
So in the last equivalence that you have, so when X is a finite complex, the modules over the chains on loops on X is equivalent to something about the cochains X, but probably not all of them. Do you understand the relationship between that and the comodules on chains on X?
I suspect it's a dual.
Yeah,
I think that that's probably exactly what's going on in that case. That if you're thinking about, let's see, because you're talking about modules over the cochains, right?
Yeah.
Right. So if I have a comodule over the chains, I can get a module over the cochains just by dualizing. To go back, that's where the finiteness comes in, because then you can dualize a module over the, my finiteness is the modules anyway. Then you can dualize that and get back to comodules. Okay. So if I have a coalgebra then I'm going to let DG co-free C be the collection of the following guys. So I don't want to have to define what quasi-co-free and co-generated are, although it's not that hard to sort of dualize what we're used to thinking about. But it turns out that the right way to think about this is you take those C comodules that are fibrant, which means essentially that you have something that's some kind of a retract of a Postnikov tower built up from co-free things. And there exists some DG free guy over this guy and a weak equivalence. So I use this functor LC to go from comodules over C to modules over omega C. And so its image under LC has to be one of these DG free guys, which gives us the finiteness kind of type of condition that we want.
So the DG frees you say with the compact objects.
Right. These are these.
Is there a comparable statement?
I think so, but I don't know. I haven't checked it yet because this is from last week. So I can check that. Getting this right. All right. So this is basically, I mean, from this we can see that there's a sort of there's very much a finiteness condition going on here because there's a finiteness condition in M. And if you think about what goes on when you had somebody who was actually co-free on this side, then it would end up being free on the same sort of generating. So there's an appropriate finiteness. Okay, so if you define it that way, then we have the following proposition. Which says that the coHochschild homology C is isomorphic to the Hochschild homology of Okay, so I'm actually going to give you a proof sketch because it's not that hard. Or I'll hide the hard part maybe instead of putting it. So how are we going to show this? So we're going to use the fact that the coHochschild complex C is equivalent to the Hochschild complex of omega C. And the work, which is like other agreement, shows that this is the Hochschild homology of DG3. And then it turns out that if you start with this DG equivalent equivalence up there, and there's a way of checking when a DG equivalent equivalence gives you what's called a quasi-equivalence of DG categories, which then it turns out that every quasi-equivalence of DG categories is in fact a Morita equivalence of DG categories. So it turns out that this is the same as DG co-free C, and so this is by Morita invariance of the Hochschild construction plus the DG equivalent equivalence above, plus a little bit of work to show that that gives you a quasi-equivalence. And then, that's it. Because you have the coHochschild complex of C equivalent to the Hochschild complex of the DG co-free thing. All right. So, we're not Morita invariance, we're on a roll here.
Did you say where you were hiding this?
I'm hiding things here. The fact that you had to get a quasi-equivalence and therefore a Morita equivalence out of a DG equivalent equivalence. This is sort of thing that should be in the literature, but we weren't able to find it, so we had to come up with some way. So what about Morita invariance in this context? So for this, I'm going to pull out some work that I did together with Alexander. working this year. So first I need to answer, what is a reasonable definition of Morida equivalence? That's the first question we need to ask. And so let me fix two coalgebras. And I'm going to define a certain notion of what we're going to mean by a special kind of homomorphism between these guys. So a braiding from C to D is this is a chain complex X plus a chain map of T from C tends to X to X tends to D, which is supposed to be appropriately compatible with the comultiplication on C and the comultiplication on D and their co-units. So, appropriately compatible with the comultiplication on C and D and their co-units. And it turns out this compatibility is such that C tensor X becomes a CD bihomology. So there's a right coaction of D that is determined by this T as long as it satisfies these conditions. It's equivalent to a right D comodal structure on C tensor X. Seen as a co-free left C comodule. Okay, so it turns out that position, if xt is a braiding into D, it gives rise to an adjunction between the corresponding comodule categories. T lower star, T upper star, such that if I apply T lower star to some comodule n, then the underlying chain complex is just n tensor X plus whatever the coaction is. Okay? So we understand this pretty well. We understand the right adjoint maybe somewhat less well, depending on the circumstances. And it turns out that this thing, in this context, we're working over, where the chain complex is over a field and everything is in an equivalent pair. With respect to the model structures and categories of homologies that I described before. And we'll say that if there is a braiding inducing now equivalent equivalence of the corresponding comodule categories, then we'll call that, we'll say that C and D are Morida equivalent. So it's really a categorification of the notion of equivalence between coalgebras. So that's why Alexander and I deemed that it was worthy to be called a Morida equivalence. So if there exists an xt from C to D like this, such that this pair is equivalent equivalence, and this will also be enriched. So it works out nicely. Then C and D are Morida equivalent. And we'll write this like this. Alright. So, and it turns out that if C and D are Morida equivalent, then their coHochschild. Homologies are equivalent. So this actually uses the proof. It's actually based on agreement. Because it turns out that one can break up this kind of Moravian equivalence into two steps, one of which is, one of which is a Moravian equivalence, the other which is an actual weak equivalence, and one can control both of these pieces very well, and one uses agreement to glue them all together. Okay, so what about the spectral world? coHHH. The spectral world. So this is finding coTHH. Okay, so I'm going to be thinking about C being some sort of coalgebra in the category spectra over some sort of commutative ring spectrum. Now, one sad thing about spectra, or at least when you insist on working with model categories, and I'm starting to realize one shouldn't always insist on working with model categories, but if you do, then you have a problem when you're thinking about strictly co-associative and particularly co-unital things, which is that there's, in fact, if you look at the suspension spectrum of the zero step, that this actually surjects onto C, which implies in particular that C is always co-commutative. This is whatever your favorite category of a model category spectra is, diagram, any kind of diagram spectra, or S modules or something like this. So everybody is co-commutative. And you may as well just take suspension spectrum spaces. And those will always be coalgebras because of the diagonal coming from X. And so, this is quite a concession for me. Maybe you should work. Oh well. But there are still interesting things to be said in this case about what's going on with suspension spectra. So before I start talking about this, let me just introduce, I should point out that, so this was originally an observation that Brooke and I made for symmetric spectra, and then Brooke and her student Maximilien Berhoum showed that this was the case no matter what your favorite category, model category spectra was. Oh well. So let me just say something about cobar constructions and coCHH, how we're going to define them. So if we have now our coalgebra spectrum, which is really just a suspension spectrum with a space, most likely, then the cobar construction is going to be a spectrum that you get by taking tot on a fibered replacement of this cocyclic cobar construction that I was talking about before. So this is tot of a fibered replacement. Again, the sort of thing you don't have to worry about if you're thinking of any categories, I guess. And, oh sorry, this is wrong. This is completely wrong. This is, right. So this is an actual cobar, cosymmetric cobar. Which in level n has a smash copy, n smash copies of C, and then the cofaces and codegeneracies are given the cofaces by using the co-unit and the codegeneracies by using the diagonal on C. And coTHH of C is the same kind of code of a fiber replacement. So let's think about the properties of these constructions now in the spectral context. So we have some kind of more elementary invariance results. For example, that this thing is going to give us is going to be homotopy invariant in the sense that if I have both of these guys were underlying co-fibrant spectra, and this is weak equivalence, then the co-HHs are equivalent, so that's good. We have a nice homotopy invariant. Again, for in the DG context, this was sort of obvious. And then another thing is that it doesn't matter which model of spectrum you choose. So with any usual model of spectrum. So it's a model invariant, which is nice to know. I know that there are different churches about which sort of model one should be using. So you can use whatever you like. So what's the relation with free loop spaces? Since that's been sort of the driving theme here, let me just say that a Kahn complex X is what we'll call EMSS for Allen-Morgan-Moore spectral sequence. Good. If, first of all, the space is connected, so X is connected, and its fundamental group acts trivially, omnipotently, sorry, on the homology groups. So we need to restrict these as EMF good spaces. So the reason we're interested in EMS good spaces is that if Fx is EMSS good, then the Allen-Morgan-Moore spectral sequence for the path vibration converges strongly. This is a desirable property for the sorts of computations that we're going to do because we need to be computing some totes. And the second thing is that, well, if you want an example, if X is one connected, it's certainly EMS good. So what we're going to do is establish some results for EMS as good spaces that are already known for simply connected spaces, for example. So, such as the following theorem. So, it's highly analogous to the results we had in the chain complex case, proved very differently. So, a theorem which, in the simply connected case by Kuhn and Markovich, and then really thanks to Brooks' familiarity with all things taught in EMSS, enabled us to extend it. So this is one connected case. So if X is EMSS good, then the topological coHochschild homology of X is equivalent to the suspension spectrum of the free loop space. This all fits into the same nice picture. And sort of parenthetically, if X is one connected, then the cobar on X is equivalent to the suspension spectrum of the base loops. So these things, these are nice generalizations of what we were seeing in the DG case, or analogs in any case. So the I'm not going to write anything down about the proof of this, but just to say that this is the importance of this EMS as good condition is just the fact that we really want to be able to commute the suspension spectrum functor through this tote functor, this tote bar functor. And that requires this kind of condition here, some nice strong convergence results with Einberg-Moore spectral sequence. But that's also has to be quite careful with base points, which was a bit of a struggle, but we got there. So, as a corollary of this, we have the following result, which is that if X is a one-connected Hahn complex, then we have a nice relationship between coTHH and THH. CoTHH of the suspension spectrum of X is equivalent to THH of the suspension spectrum of loops X. And this is because it was been on for a while, the THH of the base loops was the same thing as the suspension spectrum with the free loop space. So it goes through this result here, and due to some older work. But it's again the same kind of compatibility between coTHH and THH as we saw before. Again, with the advantage here that this guy is in some sense a little smaller than this one here. So if you actually wanted to compute something, this might be your place to start. Okay. And then there's a sort of a categorification of this, which comes from an earlier paper that Brooke and I wrote. Where we showed that there is a Coulomb equivalence between modules over suspension spectrum on base loops and comodules over suspension spectrum on X, like this, for any X connected complex. So we have a Coulomb equivalence like this, and so we again have this kind of relationship that we had before in the DG complex. And as a corollary of that, we can get agreement. So, what does this say? That if X is a one-connected Hahn complex, so recall that in the DG context we had agreement for coalgebras in general. Now we're sort of restricting to suspension spectra because that's basically all we have, as we're not working infinity categories. That coTHH of the suspension spectrum of X is equivalent to THH of the category of the fixed subcategory, the category of comodules, and I just better not make a mistake there. Yes. The suspension spectrum of X. And here, generated not by the sphere spectrum, rather than by the coalgebra itself. So, how does this work? So coTHH of the suspension spectrum of X is, by the previous result, the same as THH of suspension spectrum of loops X, which, by the result of Blomberg and Mandel, is the same thing as THH of the fixed subcategory of a category of modules over the suspension spectrum of the loops, base loops. And now, if we look at this theorem here, and we chase through what happens when we start with this guy, it turns out that if I look at the suspension spectrum of the base loops, it's sent to something that is equivalent to the sphere spectrum. Not exactly the sphere spectrum, but it's something that contracts down to the sphere spectrum. And so because of that, because we have this enriched Coulomb equivalence, that gives us this. So we really need these Coulomb equivalences to chase this through and get this agreement. So what's left as an open question here is, what about Morita? Morita invariance of there are some technical difficulties with taking the framework that Alexander and I set up and applying it in this context of spectra, similar to the kind of problems that we come up with the fact that coalgebras are basically suspension spectra. So probably, in order to get Morean invariance, which must hold, it's another thing we're going to have to probably translate to the level of infinity categories to carry it out there. In other work, we're thinking about, also we'd like to think about traces, getting a trace from the K-theory of a coalgebra to its topological coHochschild homology. And it's clear that there should be such a map, because you will have a map from the K-theory of the category of comodules, or let's say from DG co-free in the DG context, to the Hochschild homology of DG co-free. And you know that that's equivalent to the coHochschild homology of C. But it'd be really nice if you could get this sort of trace directly. And this might lead you to be able to do some computations, some trace-based methods for K-theory that are, maybe it might give you some new tools. For that, we're hoping to apply some of the methods of Jonathan Campbell and Kate Ponto with their work on bicategories and shadows and Hochschild homology as a shadow, to be able to understand these trace maps, but we'll see. And then there's also the work that Brooke and Anna-Marie and Tina and anybody else? I'm thinking about Stephanie, yes, are doing this properly with infinity categories. Thank you very much.
How strong is this result of Shipley and Peru about the suspension spectra? Like, is that for all of the extant models or anything that could be a model for?
For all extant models, I mean, do you have any more general statement, Brooke?
So in the diagram category case, I think it's stated more generally than just the 4 obvious ones, or whatever, 3, whatever it is. But no, it's not. But then it's not more general. So for diagram categories, yes. But then no, for some, yeah, that one could imagine that the models that have been set up so far have been focused on algebras, not coalgebras, and so perhaps there would be a way to set up a strict example.
So what kind of examples do you hope to get when you work?
Well, you'd like to be able to dualize some non-commutative ring spectra, for example, that to give you some examples that wouldn't be commutative. All the examples, I mean, all my favorite examples are suspension spectra, so I'm not too bothered by this, but but I'm not a stable homotopy theorist, so probably, I mean, you should be able to treat things like Spanier-Whitehead duals of things that are not commutative. That should be something that lives in your world, and it doesn't live in this world, and that's why.
What about tone spectra as twisted suspension?
Yeah, so. What'd you say, Bob?
A theory of coassociation?
I don't know. Yeah. I mean, there could be examples that are like co-associative up to homotopy that you'd like to be able to treat anyway, that you can't treat because this is really strict and it's too strict for real life. So, it's a warm-up exercise for real life.
And even in the co-commutative case, there should be things that aren't suspension spectra.
Should, because.
Well, the Spanier-Whitehead duals. I mean,
Okay.
sorry, what I mean
Yeah.
is that the current models don't have. Infinity categories of coalgebra spectra exist, and Spanier-Whitehead duals of your finite algebraic things give you examples of coalgebra spectra which are not suspension spectra.
Anybody else? Let's think. Kathryn Hess.